So if you look inside the Nintendo Wii, there's a very small chip that has the MEMS accelerometer. And if they explain what the MEMS accelerometer looks like, it's a movable mechanical structure that picks up a capacitance change when you move the actual controller. This is a very simple representation of the MEMS device. If you look at the accelerometer from analog devices, this is what the 3D model of it looks like, and it's actually quite complex. And we've removed a lot of the details of the electronics that go around it. But this is a movable mass with very complex springs that can move on top of a chip. And then the mechanical motion is changed over into an electrical signal, so with a circuit you can then do your detection of the signal. So a few years ago, we have been selling software for designing these MEMS components, and I think most of the companies that are doing MEMS know Coventor. But today, there's a lot more companies that have not been doing MEMS, they've been doing IT, and they're interested in making a product using MEMS devices, using sensors. And there's been a big problem that they couldn't get any models from the MEMS device to be able to design their ASICs. So together with Cadence, we developed a product called MEMS Plus. And MEMS Plus solves the major problem of being able in a very easy way to take a model of a 3D MEMS device and put it inside an EDA tool for electronic designs. And for this, of course, we use Cadence. So the purpose of MEMS Plus is to take the complex physics of a 3D movable structure on a silicon chip and model it mathematically to put it inside the block, so the electrical engineer can now design a circuit with the interaction of the MEMS device. And why is it so important? Well, it's important because you're trying to measure acceleration. You have a sensing element that converts the mechanical motion into an electrical signal, and then you design your signal conditioning in your ASIC. So first of all, you have to know your input signal. Well, you can measure accelerations of a human making movement, so that's quite easy. The signal conversion from the mechanical to the electrical domain you do by simulating the MEMS device, of course, and then you finally can optimize the MEMS Plus IC together. You filter the compensators, do your adjustments, your noise ratios, so you can do all the electrical things that you need to do as an IT designer. But the crucial point is, and that's where we're very strong, that you have to have accurate mathematical simulation model of the MEMS device to be able to optimize your IT. And what we do at Coventor is very unique. So in the IC world, it's very common that people, you look at a circuit and it consists of transistors, capacitors, resistors, and you connect them together with wires. In the mechanical domain, Coventor does the same thing. This is a mechanical structure. This is a dual mass gyroscope. And I will show you that here you can also stitch it together with common components such as beams and plates, cone fingers, and you can then model that and put it inside an abstract box which is called symbol. So if you look at that accelerometer again of analog devices, it's a 3D model built up of standard components. So the plate you see with the edge hole is a standard component. It's just like a designer will take a transistor from a library, you can take plates from a library in the Coventor MEMS Plus, and then you of course define the geometry. You can take suspensions like beams and springs from a standard library, and you just connect them together in 3D. You also do the electrostatic cone fingers, which take care of the conversion of movement into electrical signal. And there are of course suspensions and beams for the actual anchors, the anchor of the mass to the substrate. So what you're looking at here is the 3D user interface that a MEMS designer would use to construct the 3D model of the MEMS design. And once he does that, it's ready, and you can import the 3D schematic straight into Cadence Virtuoso, and then it's ready for simulation. So for the IC designer, this complex 3D structure becomes this small box with just electrical pins. So for the IC designer, he still works in the same environment. He doesn't really have to know whether it's a MEMS device or another IT block. For him, it looks and feels the same. Additionally, making layout is very important for us. So our software also automatically generates the layout in Cadence. So you have a parameterized layout cell of the 3D model, which is then needed if you want to go to tape out and send the file to manufacturing. So we take a closer look at this schematic block. Underneath this schematic is a very complex mathematical representation of 3D mechanics, but the IC designer, in this case I'm using MATLAB as an example, you can just do your normal control circuit around this accelerometer. And the block itself, if you look at what the pins are, well, you have the voltage and the current pin for the electrical signals, you have the acceleration that you need to apply, so this is a mechanical pin that actually has input as like the G-force as an input, and then the outputs are capacitances, which you then use in your feedback circuit. And this way, you don't have to do any finite element simulation. It's like a library of size elements or MEMS components that you can put together and simulate inside Cadence or Coventor or in MATLAB Simulink, so you're ready to stay in your own field of signal conditioning and doing your ASIC design. We believe that our model library is extremely fast. Simulations are only seconds of a complete gyroscope or an accelerometer instead of finite element analysis, which is 3D mechanical analysis, where a simulation might take hours or days. And of course, you need to have very accurate models to include nonlinearity and fringing field effects of electrostatics. And once you have that, you can do all the complex simulations like DC sweep, transient startup, and frequency sweep of the device. But when you do simulation in the IT environment, the engineers look at waveforms. So they look at these frequency blocks and voltage blocks, and they can tell how the electrical circuit is doing. A MEMS engineer doesn't understand these blocks, or it's very hard to visualize how the MEMS device will move. So additionally, we made a program you can read the output of electrical simulation and read it back into MEMS Plus, so you can visualize how the structure moves in 3D. So the electrical engineer can sign off on the MEMS part, and also the MEMS engineer can sign off on the MEMS part that the circuit is behaving correctly together with the MEMS device. So in summary, MEMS Plus has a 3D user interface to build the 3D model. This 3D schematic is then exported to Cadence, and you can import it, which automatically generates the symbol, matlist, and the parameterized layout cell. And then you can start simulating in the standard simulator, such as Cadence or MATLAB. Then we also generate the layout cell, so you actually have the route to go to fabrication. And you can read in the simulation results back into MEMS Plus. And we don't just do accelerometers. Here are a few examples of structures. And again, these are not 3D finite element simulations. These are simulations done in a circuit simulator. The first example is actually a DLP mirror from Texas Instruments that's in the projector, doing the electromechanical simulation. The second one is a complex accelerometer that's very hard to do in 3D solid modeling tools. We do ring gyroscopes, we do resonators, and of course we do RF switches for MEMS applications. So for those IT engineers that are here, they understand the red part, which is all these Cadence virtuoso tools that they normally use to design their IT circuits. And MEMS Plus is an add-on that generates all the components needed that you see here in blue, like the schematic symbol, the matlist. You supply the MEMS library, you can do all the simulations that you need to do, you supply the layout details, all these blocks that are inserted by MEMS Plus. So as an IT engineer, you now have a tool to be able to design your circuit. The key features to close this presentation, we wanted to have a 3D user interface because MEMS move in 3D and our three-dimensional structures. Everything is fully parameterized, so we don't restrict the user to being very flexible in doing material analysis or process change analysis. We leave everything as a parameter. It's integrated with standard EDA systems and EDA tools and system tools, so we didn't reinvent the simulators, and you can simulate the MEMS and IT together. Of course, I'd like to thank you, and in Taiwan we have a very good distributor